Can one of you tell me the meaning of equilibrium or the condition for equilibrium? Oh, it's already here. Fine. The force acting on the object, net force acting, has to be 0. Okay. And then we discussed 3 different types of equilibrium: stable, unstable, and neutral. You say that the equilibrium is stable if the object has a tendency to come back to the equilibrium position even if you disturb it slightly. Like you take the object to the next position on the surface and you leave it. If it has a tendency to come back to the equilibrium position, then that kind of equilibrium is called stable equilibrium. And at stable equilibrium, the potential energy of the object will be minimum. Okay. Next kind of equilibrium is unstable equilibrium, where if you take the particle to the position next to equilibrium position and leave it, it won't come back to equilibrium, it will go away from equilibrium. Okay, that kind of equilibrium is called unstable equilibrium. And at unstable equilibrium, the potential energy will be maximum. And the third kind of equilibrium, neutral, where even if you take the object to the next position and leave, the object will neither have a tendency to come to equilibrium nor go away from equilibrium. That kind of equilibrium is called neutral equilibrium. And there the potential energy is uniform, neither maximum nor minimum. Okay. Now, one of you tell me, if you have a function like y is equal to f of x, and you need to find out the maximum value of y, what are the steps? What is the first thing you need to do? If you know how y depends on x, you know the function y is equal to f of x, and you want to find out the maximum value of y, what can be done?
Differentiate.
Good. That's the first thing to do. You will differentiate the function and equate it to 0. What will you get from this? Or how will this help? Good, good. If you equate dy by dx to 0, the values of x which satisfy this condition are called critical points or critical values, you can say. Basically, at these values of x, there is a chance of the function being maximum, minimum, or constant. Okay. Whether a function is maximum or minimum or constant, the derivative, first derivative will be 0. So we make use of that to first identify where those maxima or minima can occur. Okay. What is the next thing to do? How to confirm whether a particular critical value corresponds to a maximum or a minimum?
So we get the second derivative of y.
Correct. You differentiate the function once again, d square y by dx square, and if second derivative is negative, then that critical value corresponds to a maximum. If second derivative is positive, the critical value corresponds to a minimum. If second derivative is also 0, then it means the function is uniform there. It is not changing. It's neither maximum nor minimum. We say the function is uniform. Okay, I'll explain this to you with an example. Some of you seem to have forgotten. Just one quick example we will take. Suppose y is equal to 1 second. X cube minus 5x square plus 6x. Let's say this is the function given to you. And you have to find out where the function attains maximum or minimum and also how much that maximum or minimum is. Okay, so try this, all of you. First, differentiate it and equate it to 0 and get the critical points. Do this part. In the meantime, I'll get the graph of this function. If any of you have found the critical points or critical values of x, you can tell. Okay, Pawan, what is the derivative of the given function?
3x square minus 10x plus 6.
3x square minus 10x plus 6. You have to equate this to 0. Now, this is a quadratic equation. Can you tell me the roots of this quadratic equation? What is the formula for roots of a quadratic equation?
Minus b plus or minus
Correct.
root of b square minus 4c by 2.
So here it becomes minus of b is minus 10. So minus b plus or minus under root b square is 10 square 100 minus 4ac. 4 into 3 into 6. 4 into 6 is 24 into 3 is 72. Divided by 2a, that is 2 into 3, 6. These are the two roots. You get it as 10. 100 minus 72 becomes 28. Root 28, let it be. Plus or minus root 28 divided by 6. Okay, the numbers are not that comfortable. Let it be. These are the two roots of this equation. So x is equal to 10 minus root 28 divided by 6 is one critical value, and x is equal to 10 plus root 28 by 6 is another critical value. Okay, just a moment. Okay, 10 minus root 28 by 6 is 0.784. Let it be. And 10 plus root 28 by 6 will be 2.55 approximately. Okay. We got two critical values. Now at x is equal to 0.784 or 2.55, the function can have a maximum or a minimum. One can be maximum, one can be minimum also. Okay. Now look at the graph and you yourself can see whether what we got is correct or not. This is the graph of the given function x cube minus 5x square plus 6x. Now you can see there are two critical points. They're already marked here. This is one of them where there is a maximum, and this is the other one where there is a minimum. Okay, the function is not constant anywhere. As the value of x changes, the function keeps on changing. Okay, and you can see where the maximum has occurred. Like one of the critical values, it does appear to be 0.784. Okay, so this is 0.7. It's close to 0.8 on the graph, but it's actually 0.784. Okay, that is one critical value. Where from the graph we can see and tell that it's a maximum, but mathematically also we should find out. The next critical point, you can see it is slightly beyond 2.5, and as expected, it is 2.55. This point. These are the two critical points. Okay. And we know at the first one there is a maximum, at the second one there is a minimum. We'll see if we can prove that mathematically. To check for maximum minimum, we go for the second derivative. Now the first derivative of this function is this. Then if you take second derivative, d square y by dx square, 3x square derivative is 6x, minus 10x derivative is minus 10. This is the second derivative. You don't equate this to 0. You have to see whether this is positive, negative, or 0. Okay. And to see, you have to substitute some value of x. What values you will substitute? The critical values you will substitute. Now, if you put 0.784 here, 6 into 0.784 minus 10 will definitely be negative. So at this point, the second derivative is coming out negative. And it makes sense. When second derivative is negative, the function will be maximum. Next, the other critical value of x we got is 2.55. If you put 2.55 here, 6 into 2 point something is more than 12. Minus 10, it becomes positive. So at this critical value, the second derivative d square y by dx square is turning out to be positive. So it corresponds to a minimum. Okay. So you first have to get the critical values. Those are the points where the function might be a maximum, minimum, or constant. So get those critical values first and do double differentiation and substitute these critical values to check whether they correspond to maximum or minimum. Okay, that's the idea. Let us apply that to equilibrium now. For stable equilibrium, potential energy has to be minimum. Unstable potential energy has to be maximum. Uniform potential energy has to be, for neutral equilibrium, potential energy has to be uniform. So we can draw a table like this. Stable equilibrium, unstable equilibrium, neutral equilibrium. Potential energy, if you see, at stable equilibrium, it is minimum. At unstable equilibrium, it is maximum. For neutral equilibrium, it is uniform. Means neither minimum nor maximum. Now, if a function is at its minimum or maximum or uniform, the first derivative has to be 0. Okay. So for stable equilibrium, unstable equilibrium, and neutral equilibrium, derivative of potential energy will be 0. And yesterday we discussed, last class, that force in a particular direction is negative of partial derivative of potential energy in that direction. Okay. Or with respect to position in that direction. Equilibrium itself means force being 0, no? So obviously du by dx has to be 0 for any kind of equilibrium. First derivative will be 0. Then the second derivative, if you see, d square u by dx square. Actually, we should properly write it as dou. Let us write dou only. Partial derivative we have to take. Partial derivative can be done twice also, nothing wrong in that. Dou square u by dou x square. When energy is minimum, or when any function is minimum, second derivative has to be positive. When any function is maximum, second derivative has to be negative. When any function is uniform, second derivative will also be 0. Mathematically, this is how we identify whether a particular position corresponds to stable equilibrium or unstable equilibrium or neutral equilibrium. We differentiate the potential energy function. We equate it to 0, we get the critical values. We differentiate it once again and check whether the energy is maximum, minimum, or uniform. Based on that, we can tell whether it is stable, unstable, or neutral. Okay. And dou u by dou x is nothing but negative of the force, because F is minus dou u by dou x, so dou u by dou x is minus F. Fine. So dou square u by dou x square becomes minus dou F by dou x. You have to differentiate the force. You can look at it that way also. Differentiating potential energy twice means differentiating force once. Okay. So you can comment on this also. Dou F by dou x is rate of change of force with respect to position. Fine. and there's a minus sign. So we can actually extend this table, let it be. So dou f by dou x here will be negative, positive, 0. Minus dou f by dou x is plus, minus, and 0. So dou f by dou x will be minus, plus, and 0. Okay. What does dou f by dou x, what does rate of change of a quantity being negative mean? The force must be decreasing. Quantity must be decreasing. Okay. So you can say force must be decreasing here, increasing here, uniform here. That way also you can tell. Okay, we'll solve problems you will understand. But I want you all to imagine a little bit. Now I gave you one example of equilibrium. We took two bowl-shaped surfaces and one flat surface to uh, to visualize different cases of equilibrium. Now you all come up with some other examples where an object is in stable equilibrium. Like any object which even if you disturb slightly comes back to its initial position. Can you think of such examples in real life? Any real life examples of stable equilibrium other than this? Have you ever seen any object or any system which even if disturbed slightly comes back to the original position?
Bob.
Correct. Bob suspended by a string. Good. Like a simple pendulum. Okay. You disturb it slightly, it will come back to its equilibrium position. If the frame of reference is not accelerated, or if the point of suspension is not accelerated, this is the resting position of the bob. If you disturb it slightly and release also, you know it will oscillate. It will have a tendency to come back to equilibrium. Okay, good example. Any other cases you can think of? Someone said electron. How? Can you
ఫిక్స్డ్ ఆర్బిటాల్ మీద తిరుగుతాయి కాబట్టి
what did you say?
ఫిక్స్డ్ ఆర్బిటాల్ మీద తిరుగుతుంది సార్.
No, no. See, that is there. If an electron goes around in an orbit, that is not a tendency to come back to equilibrium. It's not stopping anywhere. There's no resting position at all. Okay, it just keeps going round and round. That is not coming back. If you disturb slightly, it won't come back. No, it'll make the round and come back. That is not the coming back that we are talking about. Okay. పవన్ ఒక పొజిషన్ నుంచి పక్కన పొజిషన్లో పెట్టి రిలీజ్ చేస్తే అది మళ్ళీ ఈ పొజిషన్కి వచ్చేయాలన్నమాట. ఎలక్ట్రాన్ డస్ నాట్ డూ దట్. ఎనీ అదర్ ఎగ్జాంపుల్స్ యూ ఆల్ కెన్ థింక్ ఆఫ్? What about, okay, let me take the diagram itself. What about this case where a block is connected to a spring? Okay, rigidly connected. And it's on a horizontal surface. Let me adjust the situation. Assume this block is fixed to the spring. Now, if you leave this system at natural length, it will stay there only. So we know natural length is the equilibrium position for this. Okay. But if you pull it to the right side, spring will get elongated. It will pull the block back to equilibrium. Okay. And if you push it to the left side, spring will be compressed. It will push the block back to equilibrium. So here, the kind of equilibrium the block is experiencing is a stable equilibrium. So spring block systems, simple pendulum, You can even suspend the spring block system vertically. Suppose the system is suspended vertically like this from a fixed support. We had done this before. Let this be the natural length of the spring. From natural length, the spring has to elongate by a distance of kx is equal to mg, means x is equal to mg by k. It has to elongate that much for the block to be in equilibrium. Okay, so this is the equilibrium position of the block. Now what happens if you pull it slightly below equilibrium? Spring force will dominate and it will pull it back up. If you lift it above equilibrium, spring force will be too less, gravity will dominate, it will pull it back down, it will bring it back down. So it will oscillate around that position. So that kind of equilibrium is called stable equilibrium. Okay, so basically any oscillating system, any system that keeps going to and fro must be having a stable equilibrium position. Okay. Anyway, in 11th class itself, you have a separate chapter oscillations. In that you will learn in depth. So these are all examples of stable equilibrium itself. Next, can any of you think of an example of unstable equilibrium? Like in a particular position, the object is in equilibrium. If you disturb it slightly also, it will go away from that position and not come back. Can you think of such situations? Cases of unstable equilibrium. You just consider a rod placed vertically like this. Practically, this is difficult, but not impossible. You can balance a rod like this. Okay, but you disturb it slightly, take it to just the next position or tilt it by a small angle also, and you leave, what will happen? The rod will fall off like this. It won't go back to equilibrium. Okay, so this initial position is an equilibrium position, but that equilibrium there is unstable. Okay, even if you disturb it slightly, it goes away from the equilibrium position. Okay, you can think of many such examples. Okay. Try this question. Suppose potential energy along the x-axis varies from point to point or varies with position as u is equal to, let's say 12x square minus 6x. You are given the potential energy function. Okay. Derive the position of equilibrium, means at which position can an object be in equilibrium. And then check whether it is stable equilibrium or unstable equilibrium or neutral equilibrium. So you have to find out the type of equilibrium. Try this, all of you. Rishi, how will you identify the position of equilibrium?
So I have to find the derivative of it first.
Good. Okay. You need to take dou u by dou x. What will that be?
24x minus 6.
And what will you do with it?
Then after that, I'll have to double partial differentiate it.
So will you not do anything with the first derivative? Is it only a step to get the second derivative? Okay, Rishi, tell me, what does equilibrium mean?
Sir, when the force F net is equal to 0.
Okay, the force has to become 0. Okay, and how is force related to potential energy? Force is minus dou u by dou x. So minus dou u by dou x should become 0. That means dou u by dou x has to be equated to 0. So you get the first derivative and then you equate it to 0. If you do that, you get x is equal to 6 by 24, that is 1 by 4 or 0.25 meters. This is the position of equilibrium. This is where the object is in equilibrium. Because at this value of x, the first derivative of potential energy is becoming 0. First derivative of potential energy becoming 0 means force becoming 0. Okay, I'm telling this to all of you. And that is what equilibrium stands for. Equilibrium means. Okay. So equate the first derivative of potential energy to 0, you'll identify the position of equilibrium. Now you have to check whether it's stable, unstable, or neutral. Pawan, can you tell me how to confirm that, whether it is stable, unstable, or neutral?
The double differentiation.
Okay. And after that, like if you do double differentiation, dou square u by dou x square, it becomes 24, only 24. What can you tell based on this?
Sir, suppose అది పాజిటివ్ అయితే స్టేబుల్.
Okay, okay. 24 is anyway a positive number. Second derivative positive means the function attains a minimum at that position. Means potential energy is minimum at x is equal to 0.25. And if potential energy is minimum there, it's a position of stable equilibrium. Okay, if the second derivative is positive, it corresponds to stable equilibrium. Okay, in fact, by looking at this equation also you can tell the potential energy equation given to you is a quadratic equation. And it's a quadratic equation with the leading coefficient being positive. If the leading coefficient is positive, the graph will be like this. Therefore, the critical point corresponds to a minimum of potential energy, which in turn corresponds to stable equilibrium. That way also you could have answered. Okay. Fine, let's try another problem. Suppose a graph is given to you, graph of what and what? Let's say force at different positions. That graph is directly given to you. And the graph looks like this. Okay. This point is x is equal to a. This highest point is x is equal to b. And this point is x is equal to c. So this is how, or this is a graph of how much force acts on the object at different positions. So the question is, first part, identify the equilibrium positions. Second, find out what kind of equilibrium it is at each of these positions. Solve this carefully. Okay, any answer for equilibrium positions? Aishwarya, can you unmute? Okay, Vanilla, if you want to answer, you can.
A and C, sir.
A and C you are saying are equilibrium positions. Fine, that is correct only. See, equilibrium itself means net force being 0. So you just have to see from the graph at which points the force is becoming 0. It becomes 0 at 2 points. Force is on the y-axis. Okay. The graph cuts the x-axis at 2 points. Those are the points where y-coordinate is 0, means force is 0. So x is equal to A is one position of equilibrium. X is equal to C is another position of equilibrium. Now we have to find out the kind of equilibrium that exists at A and C. Imagine the object on an x-axis. Okay, the object is actually on the x-axis. The force graph is what you are given here. Okay. This is the position x is equal to A. Assume the object is here. Now, if you leave it at that position, no, the force acting on it is 0, it will stay there only. Fine. Now you have to find out whether it is a position of stable equilibrium or unstable equilibrium. Means you have to take it to the next position and see what happens. Think about this, all of you, and give your answer in chat. If you move it to a point after x is equal to A, you look at the graph. The graph will tell you what kind of force acts on it. Means you can tell which way the force acts on it from the graph. And based on that, you can tell whether the object is going to come back to equilibrium or go away from equilibrium or nothing is going to happen. So think about it and answer.
Sir, is it stable equilibrium?
We'll see. You type in chat. Okay, you think A is stable equilibrium. We'll see. Okay, I got one answer as unstable. I got one as stable. Rishi, did you say stable or unstable?
Stable, sir.
Okay, how did you determine that it is stable equilibrium?
Sir, because when A moves from, like it slightly moves,
When the object moves
it,
slightly away from A, yeah.
it's on the positive side, and then
What is on the positive side? Are you talking about the position of the object or are you talking about the force acting on the object?
the force acting on the object, sir.
When you take the particle to the position on the right of A, the force is positive. We can tell that from the graph. Positive force. What does force being positive mean? In which direction is the force acting? Force being positive means force acts along the positive x direction. And if force acts this way, the object will go away from equilibrium. Okay, hope this is clear to all of you. We identified the equilibrium position. If you leave the object at the equilibrium position, it stays there itself. But you take it to the right of the equilibrium position. When you go to the right of A, we see the force becoming positive from the graph. If force is positive, means it acts in the positive x direction, then that would take the object away from equilibrium. Let's take the position which is to the left of A also. Okay, you consider the position which is to the left of A. To the left of A from the graph, the force is negative. Force is negative means it is this way. Then also it will take it away from equilibrium. Therefore, the kind of equilibrium at point A is unstable equilibrium. Okay, when you move to the right, force is positive means force is also to the right. It will go off. When you move to the left, force is negative means force is also to the left. It will go off, go away from equilibrium. So it's unstable equilibrium. Okay. Think about what happens at C and give your answer in chat, all of you. Find out whether it is stable, unstable, or neutral equilibrium. Exactly at C, we know it won't move because the force is 0. If you take it to the right of C, imagine what happens. And then if you take it to the left of C also, imagine what happens. Vanilla, your answer is correct only. Okay, let's discuss. Pawan, how did you conclude that it is unstable equilibrium at C?
सर सी की लेफ्ट साइड में फोर्स इंक्रीज అవుతుంది
Force increase.
సర్ అండ్ యాక్సిస్ లో
No, wait. If you place the object on to the left of C, okay, left of C is this position. What can you say about the force here?
సర్ ఫోర్స్ ఇంక్రీజ్ అవుతుంది డిస్ప్లేస్మెంట్ డిక్రీజ్ అవుతుంది సార్ ఫర్ డిస్టెన్స్
See, no, you are thinking in the wrong way. You don't have to bother about force increasing or decreasing. You just need to know. See, how do we determine stable, unstable? When you disturb ante, take it to the next position. When you take it to the next position and release, what will the force do to that object? You have to see. So you just need to know how the force is acting, whether it is increasing or decreasing, who cares? How much force is acting on it is what we want. In which direction it is acting is what we want. Okay, don't say displacement decreasing, force increasing and all. We took it to the left side. Okay, now Pawan, tell me, is the force acting on that object positive, negative or zero?
సర్ పాజిటివ్
Positive. Force positive means it will act in this direction, to the right. So is the force trying to bring it back to equilibrium or take it away from equilibrium?
సర్ బ్రింగ్ ఇట్ బ్యాక్ టు ఈక్విలిబ్రియం
It is trying to bring it back to equilibrium because the force is positive there. Okay. Pawan, you only tell me now. So if you disturb it to the left, the object has a tendency to come back. Now you disturb it to the right. Okay. Disturbed to the right means that purple one. It is this point on the graph. At that point on the graph, is the force positive, negative or zero?
నెగటివ్
Negative. Force is negative means force acts to the left. Is it trying to bring the object back to equilibrium or take it away from equilibrium?
సర్ బ్రింగ్ ఇట్ బ్యాక్ టు ఈక్విలిబ్రియం
It will try to bring it back to equilibrium. Therefore, what kind of equilibrium exists at this position? It is stable equilibrium. Even if you leave the object at the next point, it will come back to this point. It has a tendency to come back to this point. So it corresponds to stable equilibrium. Is this clear to all of you? If you have any doubts, you can ask. So this is how you determine whether an equilibrium is stable, unstable or neutral. In this question, there is no neutral equilibrium position. One position corresponds to unstable, the other position corresponds to stable equilibrium. Okay, I'll give you more questions like this in the worksheet. Next worksheet is all about potential energy, force, types of equilibrium and all. Right. Okay, the next important part of this chapter is collisions. What are the different types of collisions? What happens during a collision? How to tell how the objects will move after collision. Okay, all those things we'll be learning here. Okay, just a moment. Suppose there's a horizontal surface like this, and you drop a ball onto it. Okay, let's say the ball is dropped from this height. Let's call it as h1. Now you all think about it and tell me, in a real life situation, when you drop a ball from a certain height, we know it will hit the ground, okay? What happens after it hits the ground?
Sir, it bounces.
Okay. Will it bounce to the same height from which it was projected? It was released.
No, sir.
Imagine it is released from rest. Okay, it won't bounce back to the same height. Now, when the ball comes into contact with the ground, okay, imagine that instant. Till then, gravity would have acted on it. The ball will speed up, and touch the ground with some speed. Okay. So it has some speed before collision. The ground is the surface with which it is colliding. Ground did not have any speed before collision. After collision also, it won't have any speed. Let it be. Tell me, what force acts between the ball and the ground during the collision? What normal force will act? Correct. The ball will experience a normal force this way. And not just the ball, the ground will also experience the same amount of normal force in this direction. Fine. Now we know from everyday experience that the ball will not bounce back to the same height from which it was dropped. Why do you think this happens? Like, see, if it is not going back to the same height, means it is losing some of its energy. What force do you think is responsible for the loss of this energy? Like if the mechanical energy of the ball is conserved, no, as the ball falls down, it loses gravitational potential energy, it gains kinetic energy. When it rebounds and goes back up, okay, during ascent, the ball loses kinetic energy, slows down, but it gains height, means it gains potential energy. But it's not going back to the same level from which it was dropped, means it has undergone some permanent loss of mechanical energy. How do you think that happened? Which force is responsible for that? Okay. Tell me, what kind of forces can cause loss of mechanical energy from a system? What kind of forces can remove mechanical energy from a system?
Sir, is it any non-conservative force?
Correct. Correct. Non-conservative forces remove mechanical energy from a system. Now, in a real life situation, we know the ball doesn't bounce back to the original height from which it was dropped. So along the way, what non-conservative force do you think acts on the ball, removing its mechanical energy permanently? Okay.
Air
In,
resistance.
good. In a real life situation, there will be air resistance. That is one factor. Any other forces which could cause loss of mechanical energy in this ball? There are. Okay, they are there.
Sir, it depends on the material of the ball, right?
Depends on the material, kind of. Yes. See, even if there had been no air resistance, the ball would not have bounced back to the original height. Basically, what happens when the ball comes into contact with the ground, they exert a force on each other, which kind of deforms the ball slightly. Okay, the ball will undergo a slight change in shape. It will undergo some flattening there. And then when it rebounds, the ball gets back its spherical shape. But in that process of getting compressed and coming back to original shape, some energy loss will happen. Okay, so there are some other internal forces responsible for this. Okay, let us discuss this point in detail first. Can internal forces remove the energy from a system. Can internal forces do work on a system? Let us check. Okay. You all tell me this. How much is the net internal force on any system? We had discussed this in the last class also, I think. How much is the net internal force on any system? If Newton's third law is valid, it is 0, correct? Okay. Assuming Newton's third law is valid, every action has equal and opposite reaction, then net internal force on a system will always be 0. Let me just show you that diagram. Not in the last class, maybe before that we discussed. Momentum conservation, those cases. Okay, this one, last class one. Net internal force on a system is always 0, because what do we mean by an internal force? One part of the system exerting a force on another part of the same system. Okay. If A exerts a force on B, then B will also exert an equal and opposite reaction on A. And those two will cancel if you look at the entire system. That way, the net internal force on a system is always 0. Like, let's call this as C, let's call this as D. Suppose C and D also exert a force on each other. They will also be equal opposite, they'll cancel, net force becomes 0. Internal forces do not contribute to the net force of a system at all. And because net internal force is always 0, we can say that internal forces. Okay, tell me, if net force is 0, which principle of physics is applicable? Which law of physics is applicable? Vanilla, don't answer. Anyone else? If net force is 0, which law is applicable, or which concept is applicable? Conservation of linear momentum. Okay. Now we know that net internal force on a system is always 0. So from this we can conclude that internal forces cannot change the momentum of a system. Cannot change the total momentum of a system. Okay. If a system's momentum is changing, it only happens due to external forces, not due to internal forces. Fine. Now the question is, can internal forces do work on the system? Do a net non-zero work on the system? Think about this carefully, all of you. Okay, let me write the question first. Can internal forces do net non-zero work on the system? See, for a force to do work, there should be force, there should be displacement. So you think of a system, the parts of which are undergoing displacement. And then you find out whether internal forces can do work or not. I got one answer as it is not possible for internal forces to do work. Okay, listen. This is slightly difficult to imagine, I agree. But Pawan, how did you say that they will not do any work?
సపోజ్ అక్కడ వర్క్ చేసినా కూడా దానికి ఆపోజిట్ ఇంకోటి ఉంది కాబట్టి అవి రెండు క్యాన్సిల్ అయిపోతాయి.
Oh, okay. You are saying even if one of the internal forces does any work, the reaction to it also will be doing work and they'll cancel. That need not be correct. Let's consider this case itself. Like your answer is half correct, but the final answer, your explanation is half correct, final answer is wrong. Listen, all of you. Let's consider two particles of this system. Okay, I'm erasing the other particles. Let's consider A and B itself. Let's say they have an attractive force among themselves. They attract each other. Gravitational attraction itself you consider. Then, under the influence of that attractive force, assume A moves to this position and B moves to this position. So the displacement of A is like this and the displacement of B is like this. Pawan, you tell me, how will you find out the sign of work done? Generally, if whether work done by a force is positive, negative, or zero, how can you tell? Pawan, how do you determine the sign of work done by a force? Okay, anyone else?
The direction.
Angle between force and displacement. Now you tell me, you can see the angles between force and displacement here. So tell me, what is the sign of work done on A? Is it positive, negative, or zero?
Sir, positive.
Positive. What is the sign of work done on B? Positive, negative, or zero?
Positive.
Positive. Then what is the sign of total work done? Is it zero, positive, or negative? Definitely it is positive. Internal forces can do net work on a system. Okay, internal forces cannot contribute, cannot change the momentum of a system, but they can definitely change the energy of a system. Okay, now consider this case, all of you. Suppose a person is simply standing. Okay, initially just standing, and the person starts to walk. Okay, I'll write the question here. A person initially at rest starts walking. When the person is at rest, kinetic energy of the person is zero. When the person starts walking, kinetic energy becomes greater than zero. Okay, moving objects have kinetic energy, no, half mv square. Means a change in kinetic energy is happening. And we know change in kinetic energy happens when some forces do work on the system. So we can conclude that some force must have done work, that too positive work. Kinetic energy is increasing, no, change is positive. So must have done positive work on the system. System is nothing but the person here. Which force do you think has done this positive work, and how do you justify that it is doing positive work? If possible, you give an explanation also. Think about this carefully, all of you. A person initially at rest starts walking, means the person gains kinetic energy. Which force is doing work on the person and giving that kinetic energy?
The friction.
Okay, Aishwarya is saying friction. We'll discuss. Aishwarya, how do you justify that friction is doing positive work on a walking person?
Sir, it acts in the same direction in which the person's walking.
Person is walking, friction acts in the same direction in which person is walking. Correct, correct. But the work done by friction there is zero. We had discussed this in our class itself, no? When a person simply walks without slipping, the work done by friction is zero. Aishwarya, just recollect and tell me why it is zero. Work done is integral F dot ds, where ds is the displacement of point of action of the force. When a person walks without slipping, friction acts on the person's foot. But when the person is walking, the foot on which the friction is acting is at rest. The foot which is placed on the ground is at rest. The rest of the body is moving. Okay, we had discussed all this. I'm not going to spend much time on this. So no, friction is not doing positive work on the walking person. Friction does zero work, in fact, if there's no slipping. Others, any answer? How is the person gaining kinetic energy? Which force is doing work on the person? The only explanation we can give is internal forces within the person's body. Okay, those are the ones doing work and producing kinetic energy. We know, like when we walk, we feel tired, no? The longer we walk, the more tired we feel. Okay, so the energy inside our body is getting used up. Friction is not giving us energy. If friction was giving us energy, why will we feel tired? We can walk for infinite distances. Okay, that is not what happens. Friction does not give us kinetic energy. Okay, it is the energy stored inside our body that is getting converted to kinetic energy, and the forces doing that are the internal forces in our body itself. So this is another example that internal forces can do a net non-zero work on a system. Okay, so remember this. Internal forces cannot disturb the momentum of a system, but they definitely can disturb the energy of a system. They can do work. They can produce heat. They can convert mechanical energy to other forms of energy. Okay, it depends on what kind of force that internal force is. If that internal force is conservative, then it won't change mechanical energy. If the internal force is non-conservative, then it will convert mechanical energy to other forms of energy. Okay, you know that if you run too fast or something, your body also gets heated up. You can feel it. Okay, so there must have been some non-conservative forces inside your body converting kinetic energy to heat or mechanical energy to heat, something like that. Okay, so remember, internal forces can do work on a system. They can do positive work, negative work, zero work, depending on how exactly the system is moving. Okay, like suppose a person is running, but the person wants to stop running. Running person has kinetic energy. Now that kinetic energy has to come down. That also should be removed by internal forces only. If the person is not slipping, friction won't do work while the person is slowing down also. Friction will act, but it won't do work. It's the internal forces within the person's body which remove that kinetic energy. Okay. So why we are discussing all this? Because these ideas are important to understand collisions clearly. When you drop a ball on the ground, the ball, when it hits the ground, undergoes some deformation. The ball gets compressed. Okay, in that process of compression and again relaxing to its original shape. Okay, consider this. Let's say this is when the ball just touches the ground. Okay, let's say this is when the ball just touches the ground. It has a velocity in the downward direction now. What will happen due to that velocity? It will get deformed a little bit. Okay, it kind of gets shaped out. Fine, and at one instant it will come to rest. And then when it bounces back, it gets back its original shape. Okay, when it completely, by the time it completely loses contact with the ground, it would have returned to its original shape. Okay, so in this process of getting compressed and again relaxing to original shape, see, getting compressed means what? Particles of the object are moving, particles of the ball are moving. And during compression, internal forces do work on those moving particles. Okay, so during this compression and relaxation process, internal forces can do work on those moving particles. And if those internal forces are non-conservative, they will permanently remove some mechanical energy from that object. Okay. Suppose those internal forces are all conservative only, then you won't see a loss of mechanical energy happening. In that case, the ball will bounce back to the original height also. In the absence of air resistance. See, air resistance is anyway non-conservative. You can't change its behavior. Okay. But you can change the behavior of forces acting within a system. Like, I mean, we can't change, but we can choose different systems having different kinds of forces internally. Okay, so if the internal forces are conservative, then there won't be a loss of mechanical energy happening. The ball will bounce back to the original height. If there are non-conservative internal forces, then when the ball undergoes compression and relaxation, some permanent loss of mechanical energy will happen. The ball cannot go back to the original height. Okay, so what Rishi was saying is correct. It depends on the material. What exactly happens during a collision or due to a collision depends on the material with which the objects are made or the colliding surfaces are made. Okay, so based on that, we define different types of collisions also. We'll talk about all that. Okay, just a moment. Let's consider two spheres. Okay, there is one common thing that you need to know that will happen during any collision. Just a moment. Okay, in the meantime, you solve this problem. This ball drop case itself. A ball of mass, let's say 2 kg. Okay, the usual tennis ball or rubber ball or even the cricket ball that we play with, it won't have that much mass, obviously. But just for the sake of the question, assume there's a ball of mass 2 kg dropped from a height of 20 meters above ground. Rebounds to a height of only 5 meters above the ground. Okay. Calculate the loss of mechanical energy due to collision. Okay, a ball dropped from 20 meters is only able to bounce back to 5 meters. Calculate the amount of mechanical energy lost due to the collision. Any answer? We are ignoring air resistance here. Whatever loss of mechanical energy happens due to collision itself. Okay, tell me, when the ball is just dropped, how much is its initial potential energy? What is the formula for gravitational potential energy?
mgh.
mgh. Okay, you can take the ground as the reference or some level you will have to fix as reference. I'll take ground as the reference. The ball was initially dropped from a height 20 meters. Okay, but it rebounds only to a height of 5 meters. So this is initial position, this is final position. initial position, its potential energy will be 2 into 10 into height is 20. It is dropped from rest, so initial kinetic energy is 0. Add both. The total mechanical energy initially becomes Ui plus Ki. 2020 is 400 joules. That's all. Finally, it only manages to rise to a height 5 meters. Then the final potential energy is mgh. Final kinetic energy is again 0. At that level, when it rises to the maximum height, it stops. Kinetic energy becomes 0. At both, final kinetic energy becomes 225 is only 100 joules. Therefore, the loss of mechanical energy is 300 joules. Loss is initial minus final. That is 300 joules is what it is losing. And all that loss would have happened due to collision itself. Now, some of you may have been trying like this. You might have tried to find out its mechanical energy just before collision and just after collision. You can do that also. Actually, that is what you are supposed to do. The question was asking you to calculate the loss in mechanical energy due to collision, no? So just before collision, how much energy it had, and just after collision, how much energy it has is what you need to consider. But during this fall, it won't lose any mechanical energy. There's no air resistance, no? So during the fall, its mechanical energy would have been constant everywhere. So initial mechanical energy is equal to the mechanical energy just before collision. And on the other side, when the ball bounces and rises up, it will have some mechanical energy just after collision. With that, it rises to a particular height. Okay. During that rise also, no loss of mechanical energy would have happened. Why? During the rise also, we didn't consider air resistance. I told you there's no air resistance. Okay. So whatever is the mechanical energy just after collision, finally, when it stops also, it will have the same amount of mechanical energy. So I used these two positions to get the answer. Okay. Anyway, these ideas will come with practice only. I'll give you some questions like this for practice in the next worksheet. Fine. Okay. So just some basic understanding of collisions is what we got in this class. Tomorrow's class, next class, tell me, shall I take tomorrow or on Sunday? Type your answer in chat, response in chat.